ROS developers, podcast the ROS developers. The ROS developers, podcast the ROS developers.
Hello, ROS developers, and welcome to the ROS Developers Podcast, the podcast that give you insights from the experts about how to program your robots with ROS. This is Ricardo from The Construct, and I would like to dedicate this episode to, all those people that are designing the behavior of the robots specifically for the RoboCup competition. So in the RoboCup competition, specifically in the RoboCup at home, you had to make a robot do some tasks at home, like bringing stuff to the person from the kitchen, and then looking for, from the cocktail in the table, and all that requires to design a specific behavior in the robot. So for all those of you that are working on that, I know how difficult it is. I dedicate this episode to all of you. And today we are going to talk about evolving state machines from the original SMACH ones. So the SMACH ones that are used for creating behaviors of robots. So we are going to talk about how to move forward this system, this SMACH system. But before going into that, let me remind you about our ROS Online Academy. And yes, at the Construct, we have created an online academy that is called the Robot Ignite Academy, which contains ROS learning paths for beginners. So we start by teaching you about Linux and Python for robotics, and then we continue teaching you all the basics of ROS concepts. So, all this about topics and services and packages and etc. So we continue this path, and then we conclude with a course that teaches you how to build your own robot and how to ROSify it, adding ROS control and many other things. So if you follow this path, then you can finally become a ROS developer. Yes? Okay, have a look. I will put a link in the show notes if you are interested. And now it's time that we talk with our interviewed person today, which is Brett Aldrich. Brett is the CEO of a company that is called REEL Robotics. And that company is still in the process of putting to the market some hardware for robots, but it is secret yet. Okay, so be patient. They are working hard and they are about to release their hardware. However, within that company, Brett has found the necessity to give a different approach to state machines inside ROS. And for that, he and his teams, they have developed SMAC. SMAC with two C's, okay? Check the show notes and then you will see the difference from the original SMACH. I pronounce it in Spanish way, but it's SMACH. In SMACH is the original one, and then SMAC is the one that Brett and his team have developed. Then today, Brett is going to explain us what is all about this SMAC and how we can use it for our robotics projects. So welcome to the podcast, Brett.
Thank you very much, Ricardo.
My pleasure to have you here. I saw your post about SMAC on the ROS Discourse. And then that's when I contact you because I found it very, very interesting.
Yeah.
Some weeks ago, right?
There was an exciting conversation that took place there. Yeah.
Yes, and I would like to start our interview here by asking you if you can explain to the audience what are state machines. Because some audience, maybe they are beginners or they never had the necessity to work with the state machine. So can you explain them? What are state machines?
Yeah, that's a great question. I think I would describe state machines as really more of a formalism that describes what actions to take in a given situation, and assuming too that then there's different actions that you would take in another situation. The simplest type of state machine is an if-else statement with a variable. And I think then you build from there into switch case statements and stuff like this. But when I think what you get when you get into a more advanced library like SMAC, you basically get that formalism that boxes everything into states, and then and in those states it describes what actions and operations you would perform given a set of circumstances, along with providing a way to transition to different states so that you can perform different actions and operations and so on and so forth.
Yeah, exactly. So it's like the robot is going to be in a given state at every point in time, and then given the state that it is going to do one action or another. So not all the actions are allowed in all the states, right?
Exactly. Okay. And I think it's generally, I generally think of it as the top, like the highest level of task planning and management for the robot.
Okay, yeah, that makes perfect sense. And how has been state machines been programmed in ROS up to now?
Yeah, that's a good question that I don't. My first guess is that it's largely with if-else statements. I think that's the most common one. Occasionally, you might go to switch case if it's a little bit more complicated. I've heard of teams that tried to do it using different nodes and messaging. I can't really describe too much about it because I never saw the systems, and from what I was told, they were terrible in terms of you quickly ran into all sorts of problems when you don't have all that information contained in one file, but I do think that it's in my opinion the lack of a dominant state machine in C++ for ROS has been a problem along with perception. Those are the two biggest holes I think ROS has at the moment. I'm hoping that SMAC can basically influence ROS by providing that, and I think it'll change. Or my hope is that it will change ROS in a number of ways.
Okay, so what is SMAC? So SMAC with SMACC. So what is SMAC, and why did you decide to build it?
Yeah, so SMAC is a state machine library, and it's written in C++, and it's based on Boost State Chart, which has many interesting features that SMAC inherits. It's mainly that it's a C++ template metaprogramming based library. I decided to build it by in looking. I think there was basically two things that I realized in looking at ROS. That one, every robot is a state machine, in my opinion. Now, people may argue with me, and it depends on what we mean by a robot. But I think for the types of robots that I'm interested, which are complex, I think it's pretty clear that every robot has a state machine at some level. And then the second one is that robots are amalgamations of numerous hardware subsystems. And so in taking those two into consideration, that led me to choose Boost State Chart over some of its over its main competitor in the Boost world, which is Boost MSM. I was also deeply influenced by SMACH. That was one of the first packages I tried when I got into ROS, and I had very high hopes for it. I feel like it in the implementation that SMACH came up a little short, and then it wasn't supported for a long time. But that was another key part, that seeing SMACH and also the interest that it generated helped push me to want to build a state machine and sort of standardize how robots are programmed. Yeah.
And then, so you mentioned several things here. So the differences with SMACH, and SMAC, the one that you built, SMAC. Then you mentioned that SMAC is, so if we want to build a state machine using SMAC, then we have to use C++, right?
Correct.
And then SMACH is for Python state machines. So, and it's a pain at the end. So at the end, building complex machines with SMACH, it's a pain, even if it's in Python, but at the end, you don't understand what is happening in there if you have any problem. Then in opposition with SMAC, so do we have any advantages on building the state machines on C++ instead of on Python?
I do. I think we do. I think you get much better determinism. I think you get a path towards real-time performance. You know, that obviously if you write something in C++, you don't get real-time, but at least you got a chance one day of upgrading it. I think there's other there was other problems with SMACH that were somewhat subtle. The concurrency, which was very important part of SMACH, and I want to give credit to. It didn't really work. I think that's the part that had the most trouble, and I think with C++ and I'm not saying that it could only be done in C++, but I think where it's handled by Boost State Chart, which has this long history of reliability, you know, we've solved that problem. And some of the ways in which they handled hierarchy and nesting in SMACH, you can have in theory infinite nesting of state machines, where that's not true in SMAC. In SMAC, because of the concept of orthogonals, only the what are called the leaf states, so the bottom level of states, have orthogonals. When you group states together in a superstate, that superstate does not have orthogonals, and so it's a different form of hierarchy. But I do think that SMACH was tremendously important, and I you know, as an early it led the way.
Yeah, exactly, led the way, because at that time we didn't have anything, so it was like fresh air in the area. But we have to evolve into more advanced things, and then so maybe SMAC is the option for that. And then you mentioned several parts right now. Several parts or several components of SMAC. Can you explain us how it is composed, a state machine using SMAC? Because you mentioned the orthogonals, then the leaves, and so on. So can you give us an idea, a picture, how it is composed? A simple, very simple SMAC state machine.
Yeah, I think there's probably two parts to view it. There's state hierarchy. And this, a lot of this is just the naming conventions we've adopted, but where you have states, and they're the leaf, they're the sort of the bottom level, right, of the hierarchy, and states have orthogonals, and orthogonals are like empty boxes where you place your physical subsystems. We'll come back to that later. But if you have multiple states that you want to group together, you place those in a superstate.
Okay.
And if you want to place superstates, group them together, we call that mode states. And there's no end. You can keep going to higher and higher levels.
Okay.
So that's the hierarchy. Then inside of the states, we have the substate architecture. And so back to a state, we have, let's say we've got a robot that has a mobile base, an arm, and a camera. Okay, so that's physical subsystems, and so we would have 3 orthogonals.
Okay, so you wait a second. So you're creating one orthogonal for each system or subsystem that the robot has, like the arm, the base, and the camera.
Correct.
Okay.
And that's general. Although we've written the library in such a way that, you know, if there's flexibility there. If developers want to try for whatever reason to use multiple multiple clients, we'll get to that in a second, in one orthogonal, you have the ability to do that. But yeah, I would say the typical implementation would be one different subsystem for every orthogonal.
Okay.
Yeah. And then once we look inside the orthogonals, that's where we place clients, and I'll refer to these as SMAC clients, and client behaviors. And the difference is that clients have a lifetime of the state machine, whereas client behaviors have a lifetime of that state. And so we have clients currently in SMAC for navigation. We've named that client Move Base Z. We also have one for Move It named Move It Z, and then we would have one for the camera, maybe like Perception, something like that.
Okay. And what are the advantages of using those SMAC clients?
Well, it dramatically simplifies the programming of state machines. This is we'll talk about things later, about putting things in separate compilation units that are, they're part of Boost State Chart. And when you hear that, you can separate things in different compilation units, it doesn't really register, right? Because that's kind of a dry thing. In the development of the clients that it really comes about, because and if somebody wants to look at this, I would say checking out the example in the reference library called SM Dan Spot Strikes Back. Mm-hmm. You can see, like in the movements, we'll do a client behavior that says something like client behavior navigate forward 10, and the robot will navigate forward 10 meters. Client behavior navigate backwards 10, and it'll go backwards 10 minutes. Client behavior undo whatever you did previously.
Wow.
And
so that's wait a second. So that means that, for example, if I am creating my SMAC state machine, if I use this navigation SMAC client, then I can forget about the whole thing about navigation, because I'm just calling in, let's say, in human terms. So move 10 meters or go to the door, and then the navigation system is going to, the navigation system has to be already set up. But once it is set up and running in the robot, then my state machine is going to use it transparently for me, for the creator of the SMAC state machine, right?
Exactly.
Okay.
Exactly. And then the Pablo put in place this really awesome component-based architecture for the clients, where we have things like ODOM trackers and other components in the client itself that allows you to switch planners from the client, change parameters. It's awesome. It's awesome. And like I said, it really simplifies the programming of the state machine, and it allows it for navigate. We've now got navigation done, and then we just wrote a new improved version for Move It, and we plan on keeping going with, like, we're going to write one for Perception. We've got another one for ROS control. We've got another one for generic ROS publishers. And it's the client library, as that grows, I imagine that being just a huge feature of SMAC. Sorry, I know we got off base here a little bit.
So basically, they are starting to look to me like small applications that can be plugged into a robot, into any robot, actually, right?
Yeah, that's right.
And how independent they are from the robot architecture, not architecture, but the robot specific components. How independent are they?
Very, and I would say too that they really increase it. One way that I've seen that in practice is when you do your error handling at the state machine level, then you're relying far less on the planners and the setting of parameters. One thing in examples that we've done, the amount of time that we've spent fiddling with the parameters of the navigation stack or move it to try to get it to do what we want to do. I hate to think of the hours spent doing it. I just take forever. You always got to run through it. But by moving that to the state machine, all of a sudden you really bypass that.
Yeah. Yes.
It also lets you use much simpler planners. This is another way that I really hope that SMAC will influence ROS, is that when let's say navigation, for example, the conversations generally are about very complicated planners like A-Star or Ackerman, and but the assumption, the implied assumption there is that you have to navigate somewhere in just one state, which isn't always true. For the SM DanceBot example in SM DanceBot Strikes Back, where we wanted to do more floor coverage, kind of like if you had a robotic vacuum cleaner, we had to write our own planners, but they were much, much simpler. Something like a forward planner and a backward planner that, if something in that forward planner, it'll go straight ahead. If something gets in the way, it'll stop, but it doesn't like figure out a way around it. You know what I mean? It's just forward and back. And then we had another one, undo. And I really think that what the state machine, I think what SMAC does is it makes states much easier to make. And so it brings down the cost of every state. And in doing so, I think we'll be able to attack our problems in smaller, you're chopping
units.
The problem up in smaller pieces, with much planners. Because the reality of these planners is, even for the experts who wrote them, they're a black box. No one knows what's going on inside them. Maybe they do at one point, but if they're trying to work on an application, it's a black box. Who knows why it works or why it doesn't?
And we don't care, actually.
Right, that's right.
And that's right. So we only want it to do its job, and that's all. And that's it. And then you also built, apart from the SMAC core system, then you also built a couple of visualizers so that they can help us to see the status of the current state machine running, right? So which ones are those?
Yeah, so we added we have an RViz plugin, but the real star of the show is the SMAC viewer. I also want to give credit to Jonathan Boren's great work with SMASH, who definitely inspired that viewer. And the viewer does two things. It allows you to visualize your state machine statically, so that you can see the entirety of your program, all the states, all the hierarchy in it, every transition, and every event that triggers that transition.
Okay.
And then the second thing it does is that it allows you to do that at runtime, which is crucial for debugging once you're in these kind of. It really makes debugging quite a bit easier, because you can see when the robot does something wrong. Let's say in Gazebo, you can look up and see what state it's in, what the previous transition was, and all of a sudden, you're just zeroed in on that code. And back to the static part of it, I think the SMAC viewer does something that really fills a hole that Boost State Chart had. In looking at the two Boost libraries, that you've got Boost State Chart, you've got Boost MSM, and then Boost SML. Although SML isn't exactly a Boost library yet, it wants to be one. But SML can be thought of as like a newer version of MSM. They're related in terms of how they operate on an architectural level. And the one big advantage that MSM had over State Chart was that you only have in MSM one global transition table. So you could know that for any state machine written in MSM, if you get to like the main file, you can see in one shot the transition table for the whole state machine. Now, there's a lot of downsides to that, because it caps the complexity of the state machine, and a whole bunch of other stuff that I've written about, and we can talk about more. But that was one thing that the Boost MSM folks could cling to as an example, right? Whereas in SMAC or Boost State Chart, because you have transition tables at every state, you can do a lot more with it, but it's very hard when you're looking at the files to figure out what the hell is going on here. But with the SMAC viewer, that problem is now solved, because you just get a visual printout of exactly what your state machine looks like. Every state, every transition mapped out. And so I think it's a very important, in terms of that style of template meta programming state machine. I think the SMAC viewer is unique in that combination, basically.
And what's the difference between the SMAC viewer and the RBIS plugin? What does the RBIS provide extra?
The RBIS just simply announces what state you're in. That's all it does.
Okay. Yeah,
and it's just in a text format. Again, for debugging and whatnot. We developed the RBIS plugin way before we got the SMAC viewer working.
Yeah, because it's like a quicker debugging tool for you, so you can see at least how it goes, and then the other one is a more in-deep image or snapshot of what is currently happening in the SMAC estimation.
Exactly.
Okay. And then you also mentioned on your website about that you have something that is called the SMAC custom course. What is that? The SMAC custom course.
So we haven't gotten to those yet, but we will.
Okay.
And the idea there is that we would basically have a fork of Boost State Chart that would be upgraded, instrumented. And then also, this would be like for clients and stuff. I'm imagining a model where a team begins using SMAC, and like I said, it's based on Boost State Chart, so they can develop their application. But at the moment where maybe they want to go into production and they want a certain level of instrumentation that isn't there with Boost State Chart, or they want to use custom memory allocators for maximum performance. That's where I'm imagining this is something that we could provide as a product to to basically meet those needs for production environments. And I mean, I don't necessarily even just mean production, because we have had robots made for production environments. I'm talking about something like a military fighter aircraft, where all of a sudden, like you're going to like a level of software deployment where, real timeness has to be guaranteed, and perhaps it's something modified a little bit to work on QNX or something like that.
Okay. Yeah. Okay.
Extremely high performance systems.
Okay, and then so let's go to the practical case that you would recommend to use SMAC. So can you, for example, at the beginning of the podcast, then I mentioned that you have I'm dedicating this podcast to the people that are building those behaviors for making a robot go to your kitchen, look for the can of Coke, then grasp it, and then bring it back. So that's a very simple. Okay, we can do this with a SMACH without problem. So in which cases do you recommend to use a SMAC that can outperform a SMACH?
I think the advantages accrue to SMAC over really almost any other state machine competitor. The advantages accrue as the number of orthogonals, and when I mean orthogonals, I mean these physical subsystems, right? As the number of orthogonals on your robot increases, as the complexity of the orthogonals on that robot increases. Meaning, if you've got something like the navigation stack versus something like a low battery sensor, like a a 3D LiDAR camera or something like this, or a pan tilt zoom, a robot arm, something is the more complex ones, SMAC works better. Also, as the frequency to which those orthogonals are changed. And what I mean here is, let's just say we're talking about an F-16 that has a weapons payload for Arctic conditions and a different weapons payload for desert conditions. Mm-hmm. You know, where you've got these modular systems, and the more often they're changed, I feel that SMAC rises and is a better fit, particularly over like boost SML type solutions in that case.
Okay, that would could that be applied, for example, for a robot that has to work in one house, and then then afterwards it has to work in another house, in a different house? So those would count as different environments with different set of parameters. So that would be a direct application?
Yeah, although I'm imagining more in the sense I was talking about, where let's say in one house it would need 3 cameras, and in the other house it would there's no lights, and so it has to do everything sonar or something.
Okay, got it.
And then the last is as the mission requirements increase, you know, where the you need more states, more hierarchy to the states, advanced recovery sequences, as the robot, let's say, is more expensive, right? And you're more afraid of damaging it. So, you know, you need this kind of additional complexity in the state machine. I think SMAC rises. And it's a weird, so that's where I imagine, you know, using SMAC more. But I will say, I do think of it kind of being a little bit of a strange dichotomy, where I imagine SMAC being a bonanza for new developers, in the sense that you can very quickly get up and running. And that's the idea of the SMAC reference library, where we have, I don't know exactly how many, I'm going to say something like 18 state machines currently, that you can just get going and run with a launch file and hack it from there. So there's that, and I don't know of any other library like that, where all of a sudden the launch file you're running in Gazebo, you've got the hardware, and we're going to keep adding more and more all the time. And a big focus in my mind is you know, in the architectural role, is how to bring in systems where we can take that to new levels, where, you know, my dream is that you would go in and, you know, you could almost like from a GUI interface say that you want to use, let's say, a ClearPath Robotics Husky, and you want a state that looks like this in this environment. Boom. You know what I mean? Like, you've already got a template of code that you can build on from there.
That would be the holy grail, I think, for ROS development.
Right? Yes. Yeah. And then I think so that's one way. And so in that sense, I'm very focused on developers that are learning with limited skills, like myself. I'm not a great coder. And this is how I program now, is I take an existing SMAC state machine and I hack it. But in terms of, you know, when we're in the design meetings and we're faced with questions like, you know, do we make this interface, let's say, simpler for people, or do we, you know, make it more complex in order to support more complicated robots? I almost always, and I mean, when I say almost, forget almost, I always go with the decision to support the most complex robots, because it's true at the end of the day that I'm more concerned with SMAC being deployed on the most important robotic systems of our era than I am about it being used by every single developer out there. You know, and I think that provides something else that very valuable for beginners, in this sense that, you know, right now it's almost like somebody may say, I'm trying to think of an example. Let's just say we're looking for a robot that's like it's a 4-wheeled robot that we're going to put a camera on. Okay. And right now we're going to have it do 4 waypoints. Okay. And So how would we do that? Well, we might want to start with something simpler in Python because you don't have to compile every time, or so you could
Yes.
just kind of it. But the minute you get to a level then that you want to add to it, you want to let's say, okay, now we want to add a robot arm onto that thing, or we want to add 2 LiDAR sensors, or we want to have it repeat that process. You basically have to scrap your code and start again. And with SMAC, what I think is a big deal is that you don't have to do that. SMAC is complicated enough that you can grow into your system. You can add more orthogonals at any time. If you need to go to real time, we've got a path for you.
Okay, then what you are depicting here to me, then it looks more, instead of a state machine, it's looking like a library of functionalities. And when you mention about orthogonals, it's like providing your robot with a set of skills that are already done and working. Does it make any sense?
Yeah, no, that's right. That's right.
Yeah. So then your vision for SMAC is going then beyond the concept of state machine, and then it's going further into more set of skills that can be mixed in a given way to perform different and many different tasks based on the hardware that the robot has, and also maybe some of the software.
And this gets into the client library, where like in terms of where my goal obviously is to get developers involved, right?
Okay.
And I see basically 2 places where that where developers can. I mean, don't get me wrong, I'm interested in people who want to improve the core of SMAC as well. Mm-hmm. But where I really see the potential for that is, one, in people writing their own state machines and contributing them back into the reference library.
Okay.
But for the more advanced developers, developing their own clients. Like a good example would be a client maybe for a localization and for language. I'm using the term client as opposed to, let's say, an action server, like Move Base is an action server for the navigation stack, and we have the Move Base Z client for SMAC, which interacts with that server. And so, as different as these different servers, have importance in ROS, like Move It and Move Base, having a client library that integrates with them, that to me is like you said, where it becomes almost like a set of skills, or that just simplifies the programming, in that particular orthogonal.
Okay, so I think I got it. Then what you are providing with SMAC is like the framework that allows the creation of a library of state machines and also a library of clients to different services, right? Because so far with SMACH or SMASH, I don't know how to pronounce that in English, so with SMACH, so you create your state machine, and then is that your state machine for this robot, for this specific application, and that's okay, so that it works and that's great. But with SMAC, then you provide this opportunity for sharing state machines and sharing clients. So you are providing with the SMAC directly a client for Move It, as you mentioned, and another one for navigation. So anybody can use that already on their own robots. So
yeah, exactly.
Does it make sense? So that would be kind of a libraries. Yeah. Okay.
I'm sorry. I didn't hear that question.
So yeah. So so what I mean is that you are providing the whole infrastructure to allow sharing of state machines and clients of skills.
Yeah, that's right. And I think I think it sort of shows that the importance of state machines, as an architectural element, and that they will definitely start to then affect through these clients, it then affects the servers. And I think that, again, one of the ways that I imagine and hope that SMAC will influence ROS is, I think the servers generally have gotten too big. I was talking to somebody knowledgeable about this the other day that told me that MoveIt is currently over 100,000 lines of code. That's amazing. It's and in doing so, MoveIt is an amazing piece of software, but when it's that large, there's an element of it being a little unwieldy. And then two, so let's just say you and I wanted to program, a node, right? Like, we're going to get started, so we create a ROS node to interact with MoveIt. And let's say we've got 200 lines of code. So now you've got this system with 200 lines of code attempting to, control a system with 100,000 lines of code. To me, it's resulted in too much of the error handling and stuff like that being, put into to MoveIt and also MoveBase. These things have their own complicated state machines inside them, and I'm saying that we would want a world where maybe, let's say if MoveIt is, instead of it being 100,000 lines, could come down to 75,000, and instead of just having, let's say, our own client where it's 200 lines of code, we're using the MoveIt Z client, which has something like 8,000 lines of code and other components like a trajectory tracker or a pose tracker that you don't have to write yourself. And then in that rebalancing, I hope to speed up ROS development. I think that's why it's important to me that whether or not people will use SMAC or not, my hope is that ROS finds a state machine library that becomes something of a standard.
Yes, I think that's a very good point. That is at present is something that is lacking ROS for state machine. So that is a big point. And then all this development that you are mentioning, it's for ROS 1 or ROS 2 or both.
So everything we've done so far is for ROS 1. We have plans to upgrade to ROS 2, and we're very excited about it. It seems like they've really done a lot of great work in ROS 2 in terms of cleaning up things related to real time. And handle threads, determinism, stuff like that. So we're really excited to take a look at that. We have some tactical plans on how we're going to do it. We don't see any major hurdles. And I'm anticipating that we'll have that done around October, somewhere in that time frame. Yeah.
Okay. Great.
Yeah.
So let us know when you have it published. Well, I will be keeping an eye, on the Discord. So I presume that you will announce there on the Discord. So I will be keeping an eye, and then maybe we can do a second interview related to what is new and what else you have provided for ROS 2. That is great. So, Brett, I think that we have everything here covered. Oh, no, just one question more. There's just one question that we didn't talk about. And now that you mentioned about ROS 2, so in ROS 2, the default way of doing state machines is by using behavior trees.
Yeah.
So what's the difference between state machines and behavior trees here? And how is it going to be work together?
So this is a very contentious subject that I didn't check out the announcement thread for SMAC on. Behavior trees originally came out of I think it was in the game Ghost, the gaming in the gaming industry, in the game Ghost, and where they were used to program non-player characters, like a little, like a goblin that's running around on the screen. And whereas SMAC comes from a very different lineage, which I'll tell briefly. So state machines were originally, the formalism of state machines originally came about in the 1950s with Mealy and Moore, and they created finite state machines, which were super, super simple, no hierarchy or anything like that. And in 1987, David Harrell developed state charts. And he did this while working as a consultant to Israeli aircraft industries. And he brought three things to state machines: orthogonality, hierarchy, and programmatic transitions. And the key, in my mind, the key thing to understand that is that, and this is my own commentary, you won't find this anywhere, but that David Harrell came up with those because it allowed him to model the behavior that was already being implemented by the human-powered state machines and fighter craft of that era. And that they had to deal with questions like, okay, so if I pull the ejection seat, but I'm on the ground, what do I do? Or if I pull the ejection handle, but our airspeed is at 500 knots, what do I do?
Yeah.
And those ideas then were later combined with C++ template metaprogramming by Andreas Huber-Dani in the Boost state chart library. And that was unique compared to Boost MSM. And I believe that this is a much stronger theoretical framework for complex robotics than non-player game characters. The thing about behavior trees, if we look at them, they never, non-player characters don't have subsystems. And to me, the primary weakness of them is that how do you do orthogonals? How do you have, multiple, how do you account for multiple systems in a modular way? There's other issues too. Behavior trees are polling based because they're based on conditions. It's almost like you navigate from condition to condition, and that brings out a polling based nature versus event based, which I would also say that for complex robotics, an event based state machine is superior, particularly in asynchronous environments, which all robots in ROS, in my opinion, are, because navigation navigation is an asynchronous act, right? Like, it's particularly on a computing era, right? If you say you're going to go from Barstow to Las Vegas, it's going to be a while before you get there, right? And so inherently
asynchronous. Yeah.
Then there's the issues of readability, which there's some commentary about that in the post. I'll say, hey, whatever anybody thinks in terms of how readable it is, that's up to them. But I think state machines are more readable. And then I would say also that state machines give you more precise control over the actions and the transitions that you take. Although it's true that that you can screw that up as a programmer. And so in that sense, I think behavior trees are probably a little bit more robust to developer error. Because if you don't, let's just say you write a transition from one state to another, but you change the name of the state, and all of a sudden there's you've got a little problem. Now, one thing though that Boost State Chart and SMAC, we deal with that problem through template metaprogramming. Boost State Chart using templates checks your state machine for validity at compile time. So to me, that's a problem that's been solved. But anyway, back to the differences with behavior trees and state machines. I do want to say that I respect the guys that are involved in behavior trees very much. I've spoken to David Ficonti. I think he's an amazing guy and a great programmer. But I do disagree. I think if we look at it from a historical, like kind of we take a step back. I think for whatever reason, there was a time in ROS without a dominant C++ based state machine
Yes.
library, and so then people immediately started jumping to the idea that, oh well, you don't need state machines. And that you can come in with behavior trees. And I don't know. I don't believe it. I don't believe it's the correct path.
It's a good point that you're putting here on the table. It's a hot point, and then we'll see. Yeah. So what I would like to know is from the audience. So what the audience think about it? What about between the state machines and behavior trees? So maybe you can leave us your comments on the show notes. So on the show notes is actually a post, it's a blog post. So you can put your comments there, your opinions, your ideas. If you can share anything related to that subject, this matter about state machines and behavior trees, because in my case, so I don't have it clear. Okay, so I still don't have it clear, and I have interviewed you, and also I have interviewed Davide Faconti about behavior trees. There is another podcast episode. And so there is, he gave me his reasons between behavior trees and state machines, and but I don't see it clear. I'm a very practical guy, so I wanted to see how it affects to my final result, which is the robot getting to the point, or getting there and grasping the object and coming back and so on. So so we'll see the opinion of the audience in that case.
Cool.
Okay.
I'd also, into the one thing that I feel that much of the discussions that took place on the thread, there isn't much there aren't many examples of behavior tree code that are openly available, and I would love to see some. I think it would really bring forward the discussion, by being able to, instead of discussing it on these theoretical levels, to actually look and see, on the ground, what implementations they did, and then what are the pros and cons for them. But I do want to say, I don't think that I'm not trying to exterminate behavior trees.
No,
or
of course.
And in fact, on the forum, and this is a project I'd love to see. I've had the idea basically of creating a behavior tree client for SMAC, where you would be able to combine.
Oh, wow, that's very cool.
SMAC with behavior trees. So anyway, if anybody's interested in doing that, please, let me know.
Yes, and also for all the ROS developers out there listening to the podcast, please, Brett, he mentioned already that he needs some support on developing this SMAC, and not only for the core, so the core, that would be great, but especially about building some clients or library of state machines also. So please contact him. I will put some contact details. So in case that you would like to contribute or you are creating any client for SMAC or state machine, you can contact Brett, and and then increase the reach of this project. Okay, is that okay, Brett?
No, that's wonderful.
Great. So Brett, so we have to close here. And we have, I think that we have given to the audience an overview about this project, SMAC. And then, that's it. So we'll put a lot of details about the SMAC and to your website, to yourself, your LinkedIn, etc. So the audience can contact and know more about the project there. So thank you very much, Brett.
Oh, thank you very much. I just want to say too, Ricardo, this has been an honor for me. I've been a long-time fan of the construct, and
thank you.
I'm just so happy we've done this. Thank you very much.
Thank you. The honor is, of course, mine, because I'm learning a lot about with you about this SMAC thing and this new subject that for me is new also. So thank you very much. Thank you, Brett. Thank you. Then before finishing, ROS developers out there, I would like to remind you that our goal is to achieve a 10x increase in the number of listeners of the podcast. So how can we achieve that? Only if you help us. So if you like the podcast, then please give us help us reach this goal by giving us 5 stars on iTunes or Stitcher, and also recommending this to your colleagues. So if you can put a review on iTunes, that would be super great. Okay, and that is all for today. So please wait for our newest episode that is going to be next week. And until then, keep pushing your ROS learning.